Welcome to this explainer. I am so glad you're here today because we are going to uncover how an incredibly simple, intuitive trick of the human mind actually powers the most advanced technology on the planet. We're talking about Bayesian statistics, the literal science of how we learn from new evidence. Let's kick things off by asking a massive, mind-boggling question. How does a spacecraft hurtling millions of miles through the dark void of space know exactly where it is? It's a staggering thought, right? But to answer it, we're actually going to look at something completely, totally ordinary. Section 1. Thinking like a Bayesian. The everyday math you already use. To understand how we navigate spacecraft, we first have to realize that you're already doing this exact math in your head. Imagine you're standing at a bus stop, waiting for your daily ride. Based on your past experience, maybe taking this exact route for months, you have what we call a prior belief. Your brain just intuitively knows there is roughly a 70% chance this bus will arrive perfectly on time and a slightly annoying 30% chance it's going to be late. That starting point, that is your prior.
But then, the environment changes. You pull out your phone, you check your transit app, and boom, a bright red alert pops up saying the bus is running 15 minutes late. This is your new evidence, and it instantly shatters your initial expectation.
Almost instantly, your brain does the math, and you update your belief. You figure there's now maybe a tiny 10% chance you'll somehow magically make up the time, and a whopping 90% chance you're going to be standing there a while. Congratulations! You didn't even need a calculator, but you just performed Bayesian updating. You took your prior knowledge, added new evidence, and created a totally new worldview.
Section 2. The math behind the mind. Formalizing intuition.
So now that we know you're already doing this naturally, let's step away from the bus stop and get into the actual math. Bayesian statistics takes that intuitive leap you just made on the sidewalk and formalizes it into a rigorous mathematical concept called Bayes' theorem. Simply put, it's a branch of statistics that mathematically updates our knowledge as new information rolls in, ultimately producing a highly accurate, updated belief.
Now, the absolutely crucial point here is that this isn't just some static, one-time formula. It's a dynamic, continuous loop. Step 1. You start with your prior, what you believed before seeing the data. Step 2. You gather evidence, which is the new information you just observed. And Step 3. You calculate the posterior, your updated belief. And then, well, that posterior just becomes your brand new prior, and the whole cycle starts over again.
Instead of just looking at a spreadsheet and asking, what does this data tell me all by itself, a Bayesian takes a step back. They ask, given my previous knowledge and this new data, what should I believe now? This mindset is the beating heart of the Bayesian thinking process, and it's fundamentally perfectly designed for dynamic systems that are constantly shifting.
Section 3. Classical versus Bayesian, a paradigm shift.
To really grasp why this is such a game changer for modern technology, think back to the classical statistics you probably learned in high school. Classical stats tries to find parameters that are fixed, but Bayesian statistics, it treats everything as living, breathing probability distributions. Classical generally only cares about the current batch of data in front of you, whereas Bayesian beautifully combines your prior history with that new data. Classical gives you a rigid point estimate, while Bayesian gives you an evolving posterior distribution. Ultimately, it asks the most practical question an engineer could possibly want. Given the data we just got, how likely is our hypothesis to actually be true?
Section 4. Navigating the stars. From buses to orbit.
Okay, let's scale this everyday concept way up. Think about satellite position estimation. Up in orbit, a GPS receiver operates exactly like you did at that bus stop. It has a prior, an expected satellite position based on where it was just a fraction of a second ago. Then it gets new evidence, a fresh GNSS measurement. It crunches these together to find the posterior, a newly updated, incredibly accurate true location. And it does this continuously, every single second. The stakes get even higher when a spacecraft is traveling millions of miles to Mars. Out in the dark, it doesn't just check one app. It constantly ingests a massive, super complex stream of new evidence from multiple onboard sensors all at once. We're talking data from star trackers reading the constellations, radio signals from ground stations back on Earth, visuals from optical cameras, and motion data from inertial measurement units, or IMUs. Because it uses Bayesian estimation, the spacecraft can seamlessly weave all these wildly different data streams together. It continuously updates its position, its velocity, and its attitude, meaning its orientation in space. And the true beauty of this is that the spacecraft does all of this completely on the fly, naturally incorporating new information without ever having to reboot or restart its entire navigational calculation from scratch.
Section 5. The Kalman Filter, the recursive estimator.
This continuous updating loop brings us to one of the absolute most critical, unsung engineering heroes of our modern era, the Kalman filter. If Bayesian statistics is the fuel, the Kalman filter is essentially a high-speed engine. It's a recursive Bayesian estimator. And what makes it so incredibly powerful is that by fusing what we predict with what we measure, it produces a combined estimate that is vastly better and way more accurate than either the prediction or the measurement could ever be on their own.
This builds a gorgeous, continuous, recursive cycle. First, you predict the next state using your system model. Second, you measure the real world using your actual sensors. Third, you update by combining that prediction and measurement. Predict, measure, update. Over and over again, thousands of times a second, constantly dialing in on the absolute truth.
Section 6. The Future of Smart Systems, AI and Beyond. Understanding this continuous recursive loop unlocks the secret to how modern intelligent systems actually perceive their environment and learn. Without Bayesian statistics, our most impressive space achievements would literally be mathematically impossible. We use this exact logic for satellite orbit determination, for calculating the insanely precise planetary landing guidance needed to drop a rover safely onto Mars, for tracking dangerous high-speed space debris, and even for forecasting volatile space weather.
But hey, it's not just up in space. Back down here on Earth, this same mathematical foundation powers the learning processes of our most cutting-edge technologies. When you hear exciting buzzwords like sensor fusion, machine learning, robotics, computer vision, and the autonomous navigation that lets self-driving cars navigate busy city streets safely, you are looking at Bayesian principles hard at work.
So the ultimate takeaway here is that Bayesian statistics allows intelligent systems to learn from new information and continuously improve. Whether you are a human standing in the rain waiting for a late bus, or a software engineer programming the ultra-complex guidance system of a Mars rover, combining your prior knowledge with new evidence is simply the ultimate, most logical way to improve your understanding of reality.
I want to leave you with this final provocative thought to ponder long after this explainer ends. If our machines are fundamentally learning by continuously updating their beliefs mathematically, getting closer and closer to the truth with every millisecond of new data, how will these Bayesian algorithms ultimately shape the absolute limits of artificial intelligence? Thank you for exploring this with me today. Keep updating those priors, and I'll see you in the next explainer.